So far we've looked at complex numbers in two forms, the Cartesian form and polar form, and hopefully you've now have an appreciation of polar form as being something that's quite useful, especially when you're multiplying and dividing complex numbers. Now, mathematician Euler, and he's got so many proofs and theorems named after him, he also dabbled in complex numbers and found a very unique property. You might have seen something called the Euler identity. Okay, and it looks something like this. E to the I pi plus 1 equals 0. So what's so special about this is, if you look carefully, it has very special values written in a way that's so simple and elegant. In fact, this is considered to be the most beautiful equation in the world by many people. And its simple elegance of just using different values can show you the power of the connection between the real and the imaginary. See, this is 1, which is an identity. And then you have 0, which is a representation. I'll just do that again. Identity. Then you have a 0, which is a representation of nothing. Okay, we'll call it the null. Then you have a couple of values over here. Pi, well, it's to deal with circles, right? Isn't it? It's a transcendental. Okay, transcendental is a very specific type of irrational number. Let's just call it irrational. Okay, you probably understand that. And also E is irrational. It's also a transcendental. Okay, so it's another special type of value. Let's not go into what those things are, but it's irrational. And then finally, you can see here it's got I, the imaginary value, which is also, you can say, is irrational because it is a square root value. It's a square root of -1. That's a complicated definition to talk about, but it is another dimension. So all of these are real values, real values, real values, real values, and then there's an imaginary value, and there's a connection between all of these with an equal sign, which is an equation. Okay, so the most beautiful equation in the world. Some people like to rewrite this form as e to the I pi equals -1, just so that you can have it with a negative value, and it's simplified, so you can actually have that property in a useful form. So this is actually a specific application of Euler's equation that he found, and this is what you need to know. So in complex numbers, you can write the cis form as e to the I theta. Okay, now I haven't written the modulus, so the modulus can just still be written in front of it as a multiplier. Okay, and that's what Euler form is. So for example, you might have a complex number that z equals 2 cis 2 pi on 3. Well, in Euler form, it's also written as 2 e to the I. We usually write the I first, then write the argument straight afterwards. Okay, so I'm just keeping with the consistent notation of having the I in front of the coefficient for the imaginary part. Okay, here's another one. You could have z equals 1 plus I equals, hang on a second, so this is Cartesian form, and I need to get it into Euler form. So this is a little bit hard to do. It's easier if you have it in polar form because you can just immediately see where the modulus and the arguments go. So I just need to quickly convert that. This is not a hard one to do. 1 plus I is 1 across and 1 up. So you should be able to see the length is root 2. And then e to the, and then the argument here is 45 degrees. So I pi on 4. Okay? And again, you can write it so that you can have the I afterwards. So that's just simply Euler form shown here. In the formula sheet, we'll just have a quick look. You can now see here they do give you the expanded version of the cis form. So that's actually written more like a Cartesian form with the components separated. Then they show the Euler form, and they show you the polar form. Okay. Now in the book you can see it says modulus argument and exponential form. So these two forms are what's called mod arg forms or modulus argument forms. Okay. So I'll just quickly mention all this vocabulary. So you've got mod arg, otherwise known as modulus argument form. Okay, so you have two types. You have the polar form and you have the Euler form. And the polar form is written as modulus of z cis argument, and Euler form is written as modulus of z e to the I argument. Okay. Finally, you can also utilize Euler form to do properties, and this gives you a second take on why multiplying complex numbers, you multiply the modulus and you add the arguments. Okay, so this is quite an easy proof to understand. Multiplying complex numbers. So you might have z equals, let's just call this one z1 equals r1 cis theta 1. Alright, so I'm just going to rewrite that in Euler form, which is r1 e to the I theta 1, and then have a second complex number which is z2, which will be r2 e to the I theta 2. So if I want to multiply these, therefore z1 z2 is r1 e to the I theta 1 times r2 e to the I theta 2, and just treat them like indices, right? This is your base, and these are the coefficients in the front. So if you remember, what you need to do is just multiply these two together. So r1, r2, and then e is raised to the I, and then you have to add the powers. Factorizing gives us r1, r2 e to the I theta 1 plus theta 2. That proves that we multiply the modulus, or moduli for plural, and over here you add the arguments. You can do a similar proof for division, and you'll remember that dividing two powers, you have to subtract the indices. Okay. Now, this is a good way to lead on to powers of complex numbers. The Euler form. Thank you to Euler for finding this. It is an awesome connection between the real numbers and the imaginary numbers. And we haven't discussed how this looks in terms of the Argand diagram. So if you drew these complex numbers and observe the patterns created, you will see something wonderful between the arguments and the modulus. You'll probably find these as you do the exercises, and they lead you through some investigations.